Hi, I'm Eric Haynes at NVIDIA now, and this is all about noise and reconstruction. Noise is one of those things we love, we hate it. You know, it's like we want to get rid of it, but then we want to use it. Anyway, so we have 4 papers. First one's going to be these guys, and William Donnelly is going to be the person presenting. He got his start in real-time graphics as an intern on the NVIDIA demo team. He's best known for variance shadow maps, co-authored with Andrew Lauritzen. After a brief 15-year detour through theoretical physics, he has returned to real-time rendering as a research scientist at EACD. William.
Thank you for the introduction. So my first paper was actually at I3D in 2006. Sadly, I was not able to attend, but I'm glad to finally be here. So thanks so much for hosting. So good. So I'm going to talk to you about FAST, which is a clever acronym for Filter Adapted Spatio-Temporal Sampling. And it's a collaboration between 3 groups at EA. Myself and Alan Wolf from the Future Graphics group at SEED, Judith Butapaga, who's from the Generative Arts Machine Learning group in Stockholm, and John Valdez, who's a rendering engineer on the Frostbite engine team. Good. So our motivation is stochastic rendering, right? It's a set of hugely powerful techniques, Monte Carlo, quasi-Monte Carlo, path tracing. They've completely taken over the offline rendering world, and they're coming for real time. Increasingly, this is the way you want to render things. And the promise is that if you take enough samples, you can converge to a correct, unbiased image. Okay. And that's the caveat if you take enough samples, but we live in the real world. So what we want is something like the upper left portion of this image here, where you have reflections, global illumination, everything. But the reality looks like the bottom right. We have sometimes a single sample per pixel if we're lucky, sometimes less. Okay, so what do we do? How do we make our images not look like a noisy mess? And there are a couple of answers, and one of them is denoising. So real-time rendering, we typically have to rely on some form of denoising. Could be as simple as an edge-aware bilateral filter, a simple blur. Could be TAA, could be some combination like SVGF, could be some very fancy neural denoising tech, but we have something there that denoises the image. Okay, but that's not the only thing that we can do. We can also rather than taking more samples, we can take smarter samples, and that's what FAST is about. So, our research question, given that we have that we're going to do some filtering, what is the optimal way to sample a rendering integrand, assuming a low sample count? Okay. And what we provide are 3 things, which I'll talk about in turn. First is a theoretical component, a sort of to be a bit bold about it, kind of a grand unified theory of noise textures, quality, underfiltering. We also provide, based on that theory, an optimizer that can generate noise textures that optimize our measure of quality. And we also provide the output of that. If you just want to plug it into an engine, you can grab some textures, I'll give the link later, and use those and get improvements to image quality just immediately. All right, so just to talk a little bit about the problem domain, what are we going to do? Effectively, we're generating random numbers, and we're storing them in textures. So what you'll do, you want to do some numerical integral, you want to do an ambient occlusion or some kind of sampling technique that requires randomness. You're going to look up in this texture. It'll be typically a 3D texture indexed by screen space and by frame number. Okay. And we need to know 2 things about what you need. The first thing is, what kind of values are you expecting out of this thing? The typical thing is just numbers between 0 and 1, and we, of course, support that. There are often you'll want something like a random unit vector, sometimes a cosine-weighted random unit vector. So we also allow for variable distributions to be baked into the texture. You also need to know some subtle things. Sometimes the number you're going to read is actually an angle, right? And in that case, you actually want to know that 360 degrees is equivalent to 0 degrees. That's kind of a special thing, and we support that too. So that's why for us, an interval and a circle are two different spaces. Okay. So that's the first thing. We need to know the sample space, the sort of range of values that live in this texture. And the second thing is, what kind of filtering are you going to do? Okay. And currently we support a sort of set of spatial and temporal filters that are typical and representative, but really it works for any filter. So a Gaussian filter is a pretty popular one. A box is much simpler. We've also gotten some really good results using a binomial filter, which is kind of a nice trade-off between the speed and compact support of a box filter with some smoothness that you get from the Gaussian. Okay. And then the temporal domain is also extremely important. So when doing something like TAA, you do an exponential moving average over time, and we support those sorts of filters. We also account for a certain probability of disocclusion events in our exponentially moving average filter, which is important. Okay. And in general, so just to preview the kind of thing that we can generate with our tool, here is a 2x2 grid of possible noise patterns that you can construct. And you can, just to show that you can independently vary the type of the samples. So on the left, you'll see just scalars, just numbers between 0 and 1, and on the right, cosine weighted hemisphere. That's why it looks like it's colored like a normal map. And you can, so going left to right, you vary the type, and going up to down, you vary the filter, and you can see the visual appearance of the noise sort of matches between the left and the right, while the values are completely different. So those are two parameters that we can independently vary. All right. So how do we generate these things? What's the theory behind it? So ideally, what you would want to do, you read your value from the texture, you carry out some numerical integration. For example, you trace rays. Here we're doing ambient occlusion, and then you filter. Okay. The idea is we want to minimize noise in the final image by modifying the values on the far left. In order to do this, obviously, you have to backpropagate through the filtering and the rendering. But we, rather than hook this thing up to a renderer, we make some key simplifications that allow us to use an analytical model. And there are two simplifications. The first one is that our rendering integral gets replaced with a random Heaviside function. This is a pretty standard model for emulating the types of discontinuous functions that you typically see in rendering. So a major source of rendering noise is visibility queries, which are 0, 1 valued. And so we use random Heaviside functions to model that coherent but discontinuous quality of typical rendering integrands. We assume a linear filter is another key thing. Obviously, filters are not quite linear. They're edge aware. There's some randomness involved, but a linear filter actually makes a good approximation of what a sort of ideal filtering is. And finally, the thing that we want to minimize, the error in the final image we measure with our MSE, that isn't the best perceptual metric, but if you're just measuring the quantity of noise in an image, it works quite well. So those are the three key assumptions. And under those assumptions, we can actually just write down a loss function that analytically captures all of this. And it turns out that, so it takes this extremely simple form, even though there are some integrals that went into it. You just wind up summing over pairs of pixels in the image. You need to look at the overlap between the filter of those 2 points. So nearby images, this FJK will be, or nearby points in the image will have this FJK be larger. And then the negative of the distance between the values in the texture. So this is, I think, quite intuitive. If you have 2 nearby points on the image plane, you want to take samples that are as far apart. You want to trace rays that are in different directions. The main source of inefficiency in white noise random number generator comes from the sort of clumping of values where you sometimes will trace rays in similar directions and get positively correlated results. Here we arrange for the minimum amount of correlation. Okay. And our algorithm is actually very simple. It's just based on swapping. So Heitz and Belcourt used a similar one. Wolf et al. Used a similar one in their paper about spatio-temporal blue noise. Here, what we do is we parallelize it so it runs on the GPU. You need to tell it your sample space and distribution. So here we're generating one of my favorite fast noise textures. It's a cosine weighted sphere sample optimized for a binomial filter. It's operated for an exponential moving average over time with an alpha of 0.1. There's this option of how you combine the filters. By default, it's by a product. That's what our analysis shows is optimal, given that you do both. You do a spatial filter followed by a temporal filter, but you can also combine them via a sum that generates something closer to spatio-temporal blue noise. And then you specify an output size and file, and it generates some images that you can plug straight into your renderer. So we have some examples at this URL. Our noise generator is online, and you can just grab the textures, and they're just textures, so you can plug them right into your engine now. Okay. So I just want to talk a little bit about why it works. So the image on the left is the result of a sort of synthetic rendering experiment. What we do is we take a noise texture that was optimized toward a 5x5 box filter, and we threshold it at different values, generating different simulated rendering outputs for a thresholding type of operation. And then we take the Fourier transform over all those instances and average it. And so you get this Fourier spectrum on the left. And if you look at that spectrum and you look at the spectrum of the 5x5 box filter, you see that the noise is near 0 where the filter has a support. And what that means is when you blur the result of the rendering with your 5x5 box filter, the noise just disappears. So the way it's working is that it's shaping the spectrum of the final rendering noise to be optimally removed by the filter that you specified. So that's it. That's in theory, that's a synthetic experiment. What does it look like in practice? So here are some rendering results that we presented in our paper. They're not a complete set of all the things you could do with FAST, but they're, I think, a representative sample. So on the left, we're doing ray-traced ambient occlusion. So we're using a cosine-weighted fast noise optimized for a binomial filter. So in the bottom, I have two insets. On the left, you see the raw noise, and on the right, you see the Fourier spectra. And while, unlike the synthetic experiment, you see there's actually a signal there. It's not spatially independent. You see that the noise itself you can still see the shape of the filter in the noise. The second example we considered was 1 bit per pixel dithering. So you take your image and you do the sort of most brutal truncation of the RGB channels you could possibly consider, which is down to a single bit. And so we use a 3 vector of random numbers. And this particular one is optimized for a 3x3 box filter. So the shape of the filter still comes through. It's got a sort of more square shape than the binomial. And the third example is volumetric ray marching. So in this case, we take a random scalar offset per pixel to bias the direction of the offset of our ray march. And this one, it's a little harder to see the filter, and that's because the cloud itself is fairly noisy. It has there's actual signal on all frequencies, but you can still see the shadow of the Gaussian filter that it was optimized for. So it's not just so we find that the theory matches pretty well with the practice, that actually the filter is reflected in the noise. And finally, I'd like to talk about a more challenging example with motion, which I think is somewhere where FAST is really helpful. So we compared with white noise as a baseline. That's this line in blue on the left. We compared with 2 recent implementations of this type of spatio-temporal noise, so one by Korak et al. From this past year, and spatio-temporal blue noise. And the experiment is the following. So we have this model of a car in which we're doing ray traced ambient occlusion. The graph on the left is frames going from 0 to 60, or 0 to 59, 60 frames. We start with the camera still, and as you can see, the different noises converge. Fast starts off converging a little bit faster than the others. After the filter has settled down, once you've taken about 30 samples, everything except for white noise has basically converged to the same value. So where the difference lies is when you start to move around, when you start to have disocclusions. So at around frame 29, we pan the camera over, and there are a whole bunch of disocclusion events. So if you look at the images on the right, you'll see the car after we've moved the camera over, and the right edge of the image is noisy because it had to start the filter all over again. It reprojected off the screen. It has no results there. And what we find is that the fast is able to keep a lower error in these events because it's optimized not toward the final result of the full filter, but because we are optimizing we allow for the possibility of the filter to be reset. We allow for a certain probability of disocclusion. So that wraps up my talk. So the conclusion is that we see that low sample count rendering really benefits from smart sampling. If you only have one ray to trace per pixel, then you better make sure you pick the right one. And FAST solves this problem, tells you how to choose your array, and it does so by shaping the spectrum of the noise of your final image to match the denoising filter that you're going to use on it. So I've shown some representative examples of cases where you might use this, but there are a lot of possible use cases. Stochastic rendering is everywhere, and so I encourage you to try it out. The URL is here, and the code for our generator is available, as well as a bunch of textures that you can just start plugging in right away. So thank you very much.
Do we have questions?
So thank you. The problem that you solved seems a lot more general than the domain you chose to solve it in. Can you, first of all, is that true? And second, can you think of other examples other than stochastic rendering in this case?
Yeah, that's a really good question. I mean, the use of filtering, I think, is kind of special to the domain. So it's true that in general, low discrepancy sampling, which is really what we're doing, is it's useful anywhere you use Monte Carlo, which is way beyond just graphics. The thing that's a bit unique to graphics is the filtering of results, which I don't know whether other problems. I can't think of another domain where that specific feature comes up, but probably there are some. I know that one application that's especially interesting is in machine learning, specifically in diffusion models. So in diffusion models, what you do is you generate, so typically what you do is you start with an image of pure Gaussian white noise, and you run a big network that tries to march you toward the space of natural images that follow the prompt you put in. What has been shown recently is actually adjusting the spectrum of the noise in that process can lead to better generation. I don't know that there's a great theory yet of exactly what is the best spectrum of noise to use over the course of your diffusion run. Probably at probably at the start of your run, you want to use things that have a lot of low frequencies to kind of block in the thing. And then once you're really converging on the final detail, you want to put high frequency noise. But I think that's an extremely interesting open domain where this could be applied.
Hey, awesome work. When Alan published it or posted it on social media, I got so excited I had to read the paper. And I have a question that's related to this. So my understanding is that similarly to those blue noise dithered masks, you achieve results using non-differentiable process, aka simulated annealing, by swapping the elements.
That's correct.
So given this, I would imagine that, so you mentioned that you've done some simplifications, like assume that you're using linear filters, assume that you're using this heaviside theta as your visibility, etc. Would this also approach work, like, let's say, for real rendered sequence, given that you're using this non-differentiable process that's based on swapping values? Obviously, it would be orders of magnitude slower, but I wonder, like, if the results, do you have any insight if there could be any benefit from it? And would the results, would they differ, and how much? Yeah, thank you.
Yeah, that's a really good question. So I think absolutely you could do that. So yes, so far we made two, so we made three assumptions, and you should question all of them, right? So the first assumption is random heaviside functions. One thing that I think, an option that I mentioned and could be tried is that you could just hook this up to a renderer and use some non-differentiable optimization on it. I think there's probably a clever intermediate thing you could do, which is to measure. So is basically to put in a proxy for this function that I wrote down, this distance, right, which is derived based on heaviside functions. What that thing actually is it's a 2-point correlation function between two values. That's something that you could measure in your renderer, right? So basically you just trace two rays, and based on the distance, what's the probability, what's the correlation between the values there? And you'll get some function that generally is going to be decreasing. And you can plug that into this optimizer, and maybe you will get better results, I don't know. So I think that would be an interesting thing to do. Similarly with the filtering. So we had to make some assumptions about the filter. And really, those are the sort of maximally optimistic assumptions. Your filter always gets cut off, and also you're not solving the same rendering integral at every pixel. That you have natural variation in your image. So what you could replace that with as well is a sort of expected filter value, meaning like what's the probability that a pixel, 2 pixels over is actually going to wind up contributing in my filter, versus what's the probability that it got cut off. You could also do that in time, right? What's the probability that I had clipping, or my TAA got rejected, its history, that sort of thing. So you could also measure that. So you could try to, see what benefit you could get from that. So we made sort of the 0th order approximation of an idealized model, but I think it's worth comparing what that would be like, what gains you would get by actually measuring those quantities. Yeah.
Okay, I think we're going to move on to the next. Obviously, we can question these guys after. Thanks very much. Let's thank our speaker again. So the next paper is going to be presented by Bart Wronski, and he started his career as a game developer working at CG Project Red, Ubisoft Montreal, and Sony Santa Monica. He's done the whole tour. He spent 8 years in all roles, from junior programmer to studio technical director, focusing on graphics, engine, tools, and content pipelines. Then he took almost a 5-year break from computer graphics, working in Google research on computational photography, image processing, and machine learning. He co-invented handheld multi-frame super resolution and night sight for the Google Pixel smartphones. In 2022, Bart joined NVIDIA as a principal research scientist with a mission to further connect real-time rendering, machine learning, and signal and image processing. Here's Bart.
Thank you. Today, I'm going to talk about filtering after shading with stochastic texture filtering. And this was work done as collaboration between Matt, Marco, and I from NVIDIA, and Marcos Fajardo, who's right now an independent researcher, but many of you will recognize him for his seminal work in production offline renderers. So let's start with talking about textures. Hopefully, I don't have to convince you that textures are one of the most basic and essential building blocks of computer graphics, because they can very efficiently and compactly store information about rich surface detail. They compress very well. There are lots of great tools to edit them, and they are independent of the geometric density. But what is a texture? Texture is a grid of discrete values. However, those values are defined only at texel centers, because let's remember, pixel is not a little square and texel is neither a little square. Instead, there are those infinitely small points, mathematically known as Dirac deltas. So in practice, to be able to use a texture, we cannot rely just on those values. We have to do filtering and interpolation. And in practice, this is weighted averaging of multiple texture samples, where the weights depend on the relative position of the shaded point and texels. And the same approach applies to minification, where many texels might cover single pixel. It can be thousands or maybe million texels, and we could read all of them and average them, full filtering, and some offline renderers do this. But it can be very slow, and it's higher quality than the alternative, often done in real-time rendering, of pre-filtering, creating so-called pyramids of mipmaps, mipmap chains, which is very fast, saves on memory bandwidth. However, it can be very blurry, so even real-time rendering often uses a hybrid, like combining mip mapping with anisotropic filtering or negative mip bias. And what I've described so far is common knowledge. It's almost axiomatic. You don't question it. All modern graphic APIs standardize filtering this way, like with bilinear filters. And if you read my blog, you know I really hate bilinear filters or anisotropic filters. And they are not just in APIs. They're also done in hardware. So very often for most formats, you can do filtering at zero additional cost. So it's so convenient and so cheap to use that it creates this feedback loop of, yeah, I'll just use it. I'm not going to think too much about this. You're going to think about this when either you have a problem or when you cannot use hardware filtering, which was exactly our motivation to start looking at this problem. We started to look at this last year or a year and a half ago, working on random access neural compression of material textures, which was published at SIGGRAPH 2023. When we compress whole material stacks of multiple textures to get significant compression ratios up to 16 times more texels than comparable size BC textures. And unlike other approaches, we didn't want to just load those and transcode them during streaming or virtual texture. We wanted to be able to read them in pixel shader or ray tracing shader. And we showed that even at 4K screen resolution, you can do this in 0.6 milliseconds. However, we have a problem that this representation obviously is new compression format. It does not support bilinear or trilinear filtering, and we would not want to load the cost at 8 times for trilinear filter. So instead, what we did is the stochastic filtering approach, where we jitter the UVs and then follow it by nearest neighbor sampling. I'll describe this approach in more detail in a second. And I'll also mention here that the history of stochastic filtering is very long. Even in video games, it's dating early 90s and early Star Trek game and first Unreal Engine and lots of uses in film industry, etc. So we were not the first to do this. However, in this work right now, we will generalize those, formalize, and propose 2 separate families of techniques beyond simple filters, including negative weights, negative lobe filters. But we have a much more important problem to solve first. Namely, that filtering this way changes the results. And it can change the results quite dramatically. And we started to have almost heated discussions. Which way is correct? And as a follow-up question that's bold or maybe even arrogant, are we teaching and using the texture filtering incorrectly? And to define what is correct or not, we need to make some assumptions. But first, we're going to review some literature and historical precedents. So the first very interesting precedent that we found of someone noticing that you cannot really use traditional texture filtering for nonlinear operation was Porter and Duff, when they introduced the concept of premultiplied alpha. Namely, they noticed that if you filter color and filter alpha separately, you multiply them, you end up with those ugly halos and artifacts. And this is because filtering and nonlinear operations, functions such as multiplication, they do not commute. You cannot swap the order of them arbitrarily and expect the same results. So instead, they say, hey, let's do the shading first. Let's multiply color with the alpha, and then it filters perfectly and everything works out. The next paper that was about a very different topic but made a very similar observation was Reeves et al. From SIGGRAPH 1987, paper as old as I am, where they introduced percentage closer shadow filtering, and they also noticed that for shadow maps you cannot filter depth values because the filtered average depth is nonsensical, does not correspond to any real depth in the scene, and then if you try to do nonlinear operations of depth comparison, you end up with artifacts and ugly results that are not filtered shadows. Instead, they say, hey, let's apply shading and nonlinearity first. Let's first do the comparison, creating this binary mask, which then can be filtered and averaged, and everything's works fine. And I'll add here some interesting connection that in practice, very often this filter is realized through also UV jittering, especially in real-time renderers, so actually evaluated stochastically. And they end the paper with this very interesting paragraph, where they observe that their results should generalize further, that they should not apply just to shadow maps, that one should investigate all uses of textures in computer graphics and rendering. And they give an example of problem of so-called specular aliasing. I will not go into too much detail here. I'll just mention that this is a very well-studied problem, and lots of great papers and papers are still coming even this year about this specific topic, and they are based on some adjustments of mipmap chains to preserve the appearance of specular. But to my knowledge, no one tried to answer this more general question from Reeves et al. And it's not just some historical question, it's still relevant because, for example, this problem of filtering creates ugly halos in so-called metalness workflow in PBR rendering and prevents its wider adoption. So to sum up our motivation to look into this problem, we noticed that texture filtering theory and practice were developed for interpolating just color, and in early work it was not even gamma corrected. And filtering and some affine functions, they commute perfectly. You can swap order arbitrarily. It's mathematically equivalent. It doesn't introduce errors. And however, any nonlinearity, any nonlinear function and filtering, they do not commute. And swapping order results in error or bias. So we'll make one assumption here, that textures are authored by artists with 1-to-1 pixel-to-pixel ratio. And this is not a very strong assumption. It's valid in most cases. I'll show some examples where it doesn't hold and breaks our technique and assumptions. But assuming that this is true, minifying or magnifying textures before nonlinear shading will introduce bias and error. And the different techniques were proposed to address specific types of errors. However, we want to look if we can do better in general, and we are trying to answer this question from 37 years ago. So let's have a look quickly at our well-known rendering equation. Here we have, this is just one example, but here we have an integral that corresponds to shading. We have incoming light directions. We have a reflectance function. However, reflectance function itself is typically spatially varying. It depends on, for example, textures. And the reflectance function is an integral or multiple integrals itself corresponding to texture filtering. And we already saw from this earlier work that filtering before shading, so this first applying filters integrals for texture filtering and then shading, it creates errors and in many cases and produces wrong appearance preservation or no appearance preservation. So what we propose instead is to do filtering after shading, where you swap order of integrals. And here is just a quick teaser where even our approximate real-time implementation is significantly closer to the reference when it comes to appearance preservation. However, how do we realize this integral in practice? What would it even mean, for example, for multiple UV sets? And it's clear that trying to do this brute force is going to be very slow. So instead, we propose to solve it as we solve most problems in computer graphics, with Monte Carlo. So one can take samples from this integral, and here I'm gonna go a bit fast, but I'll refer you to the paper for details. We can construct an unbiased estimator for this integral, and each sample from this estimator is equivalent to unfiltered single texel lookups. And one can take multiple samples from this estimator, and for example, for negative lobe filters, we propose a technique called positivization and taking exactly 2 samples. But in the extreme case, like we did in our texture compression paper, you can take just literally single sample. Would it be noisy? Of course. What were we expecting? However, this is single frame and white noise. If we combine it with spatio-temporal blue noise, we get significantly less noise appearance. If we combine it with DLSS as a robust temporal integrator, we get almost no noise. And when both are combined, we don't see any noise in most typical content. And in the paper, we introduced 2 families of methods. The first family operates on this observation that this integral actually corresponds to multiplying something with a bunch of Dirac deltas. So this integral is actually a sum. And we can choose a sample from this filtering sum with probability proportional to the filter value, or for mixed weights, mixed sign filters with absolute value, which is exactly importance sampling. And we can do this either from an array of weights or online through weighted reservoir sampling. And again, details are in the paper. And this approach works pretty well, but with large filters, it can be very costly because you need to do lots of filter evaluations. And even if the filter is separable, it can be a lot of additional cost. And it does not support infinite filters. You need to window them or truncate them, etc. And there is a different way, which I already mentioned, and most of prior work was using, which is this UV jitter followed by nearest neighbor sampling, which we will call filter importance sampling. And to understand this method, let's have a look what happens when you take a nearest neighbor sample. When you do this, it's equivalent to convolving Dirac deltas with a box filter. So now, if you apply uniform UV jitter, followed by nearest neighbor snapping to the closest neighbor, it's like convolving 2 box kernels, which is exactly a linear or tangent kernel. So doing it this way yields linear or bilinear, trilinear, etc. interpolation. And this is exact result from previous papers. However, we can take any jittering PDF. For example, we can use Cox-de Boer recurrent B-spline formula and jitter according to, for example, quadratic B-spline PDF followed by nearest neighbor sampling. And this yields bicubic or tricubic B-spline interpolation, which is high quality and very often used in film world. So this is pretty cool because this box filter is actually desirable and it serves as optimization because you can sample from your PDF that's degree n-1 B-spline, so it's even faster. And you're not limited to just B-spline family PDFs. You can sample even infinite spatial support filters, and you would just jitter your UVs according to the original filter PDF deconvolved with the box that will happen as a result of nearest neighbor. And even for filters that don't have any deconvolution with the box kernel, like Gaussian, you can do this, and it can be actually beneficial. And here for results, I'll refer you to the paper and explanation. Why is that so? So the main difference between those 2 different families is that one operates on the discrete filter weights and discrete kernels, the other one in the continuous filter PDFs. And in some cases, if you have just arbitrary discrete weights and kernels, or you want to use this technique of positivization, you have to use the discrete domain. But in all the other cases, we recommend using this continuous approach filter importance sampling, mainly due to much simpler implementation, which we provide in the supplementary material. It can be literally just 3 lines of code. And we could use exactly the same approach for minification, finding projected ellipsoids or trapezoids in the UV space. But there's a much simpler method that most of you who work in rendering probably already use. Namely, that if you jitter the camera projection matrix for your anti-aliasing reconstruction filter, like TAA or DLSS, or it's even used in offline renderers for ray jittering, this projects in the UV space, texture space, exactly to the coverage that we want for minification. So we don't need to do anything there. If you disable MIP maps, you have your camera jitter, you get minification, super sampling, and filtering after shading. And I bet many of you probably use this in practice and observed how it nicely can anti-alias specular. And so we don't need to do anything there. We just add this small magnification translation UV jitter, and we get very simple, minimal handling of minification and magnification. And this way, we obviously change the appearance. This is what started our investigations. And for minification, it provides nice anti-aliasing. However, for magnification, it can change the results of, for example, specular significantly. So here you can see that filtering after shading does not produce these specular peaks. And it's straightforward to understand the way that filtering before shading interpolates normals, interpolating the surface curvature. In this case, producing this sharp specular peak in the interpolated region, while filtering after shading evaluates only the directions that were present in the normal map. And neither of them produces this very sharp specular peak, so you don't get it. And in this case, I would argue that the latter is better, but it's not fundamentally good or bad, because it depends on the artist's intent and assumption. If artists really looked at pixels and texels with 1-to-1 ratio, then I would argue that this filtering after shading is better. However, if artists relied on smooth surface interpolation and they wanted to compress the textures by reducing their size and assume that it will be smooth after interpolation, then it breaks. So it changes the appearance, and artists need to be aware. And there is a much worse result from magnification filtering after shading, namely that it can amplify or show higher aliasing. And unfortunately, I would love to talk about this, but I don't have time, so I'll give you just bird's eye view explanation. It's that any nonlinear function always introduces new higher signal frequencies known as harmonics. When you apply those to the discrete signals, and those harmonics exceed your Nyquist limit, they alias immediately. So any nonlinearity will always or almost always introduce aliasing. And for magnification, screen Nyquist is higher than texture Nyquist. So if you're doing this in texture space, you're going to hit aliasing earlier. And for formal signal processing analysis, please see the paper supplement. I'm getting short on time, but I'll quickly get through the results. So I've shown some variants of this figure already a few times, and in all cases, filtering after shading is better at preserving the appearance. However, in practice for real-time rendering, we propose to still use some MIP maps, mainly to avoid cache trashing and for performance, and we do some performance analysis in the paper as well. Appearance preservation can be even more dramatic, like in this case of offline rendering and emissive volumes. If we compare the A and C, which is traditional trilinear, the results are dramatically different for minification and magnification, unacceptably so. And with stochastic filtering, they are, if you squint your eyes, they're virtually identical, so it's much better for appearance preservation. And in offline use, something that's very interesting is that you can not only get higher quality filters, for example, using stochastic tricubic instead of trilinear, it can serve as significant performance optimization, and there is no additional noise. And this surprised us, but the reason is that the volumetric Monte Carlo integration noise is so much higher than any stochastic texture filtering noise that noise is just not visible there. Additional noise is not visible there. So there is literally no cost, only benefits to using this approach. And how does it work in motion with DLSS? It works, I think, very well. In this example, representative of normal type of asset, there is no ghosting, no noise, no flickering, nothing. And because we use stochastic bicubic, arguably up close with the magnification results are much more pleasant. When we stress test it, we can produce more noise. There can be some leftover noise, especially when using stochastic bicubic because it's a wider spatial support filter. However, it's not flickering in motion, it's quite stable, and we believe that with improvements of temporal filters and improvements of spatio-temporal blue noise, like one presented just this session, we believe that it shouldn't be a problem in practice, and every year it will get better. Some recommendations. For minification, we always recommend doing filtering after shading. However, for real-time rendering, because of performance and cache friendliness, we still recommend a hybrid that is better for performance and temporal stability, but allows for some of this bias to remain. And for magnifications, there are pros and cons. Pros are that it's unbiased, it removes errors, it simplifies logic, like you don't need to take care of premultiplied alpha. You can apply metalness workflow. For virtual textures, you can get rid of the padding, etc. And it allows for better filters and new compressed texture representations like our neural texture compression. However, it can introduce aliasing, it can change the look, so it depends. Decide based on your use case, content type, etc. And you don't have to go all in. We recommend being pragmatic, and namely, you can even choose per asset if you use stochastic texture filtering or not. And for example, don't ever stochastically sample something that relies on interpolation, like side distance field fonts. Yeah. To conclude, our proposal might seem radical, but we formalize decades of observations from games, from film industry, that filtering after shading is unbiased and better for appearance preservation. And I think that we really need to change the way we teach filtering and blending of texture values, because we no longer really blend colors. Those are physical properties and very nonlinear functions, and old school approach does not work. Similarly, stochastic texture filtering was also present for decades, but we explained those prior approaches and we introduced two families of techniques with different trade-offs. We expand those to more filters, including negative lobe filters, and the source code is really minimal. It's few lines of code, so anyone can try it even today. And we believe that stochastic filtering and filtering after shading, it's a very valuable tool. It can remove workarounds and simplify codes. It enables efficient filtering of novel compression and storage formats. It allows for efficient implementation of much higher quality filters. And it has use beyond just textures. For example, one can stochastically sample complex shader graphs. And I know that some game developers were already doing this for triplanar mapping. And we argue that it actually makes sense and it's the right way to go, not to blend BRDF values, but to stochastically sample and blend lighting. And whether you're intrigued, disagree, or maybe you're outraged by our audacity, let's chat. Thank you.
Thanks. And any questions?
So, given that you have a 40-year-old paper from like a shadow mapping, 40-year-old paragraph from a shadow mapping paper, have you tried something like this on a shadow map, for instance?
I mean, it's already used on shadow maps, right? Like it's exactly the same approach. We just generalize it. It's already used. If you use the PCF type filtering, you're already doing exactly this approach, right? Yeah. I mean, no. I mean, this is. I'll mention, for example, one of the shadow map related limitations to our technique. If someone, for example, uses alpha masks for shadow maps, then if they come up very close to shadow and they start hitting this magnification, then this is where aliasing can happen and can appear, especially when using stochastic bilinear variant of the filter. Then you can observe blockiness, and this is again related to this very high nonlinearity of binary comparison. It generates infinite harmonics, so it aliases very easily. However, if, for example, you use a stochastic bicubic filter that we propose on alpha masks for shadow maps, you get for free something that's very similar to PCF and looks pretty good. So yeah.
Other questions? Great.
Yeah, this is really cool work, and I do believe you. It's yeah, super cool. My students, though, they already hate temporal anti-aliasing for a bunch of reasons. They don't like to see any kind of ghosting, and they don't like it when they see new noise appearing. And won't this lead to even more noise appearing when I suddenly move the camera, if even textures are?
Yes, it definitely can increase the appearance of noise, and it's also challenging given that many denoisers rely on noise-free guide buffers. And now we are introducing noise to guide buffers. So it makes it more challenging for those bilateral style guided denoisers, and it definitely can increase the noise. However, we tested it with DLSS, and it just worked fine to our surprise. And techniques like DLSS, but there are also many papers from Intel and others that also introduce machine learning based denoisers. They are data driven. So once you start introducing patterns like this in the training data and inform denoiser about this, I really think that it's going to only get better. And I sympathize with your students, and unfortunately, I think that the ship has sailed.
Yeah, I agree. Great work, thank you.
Thank you. Amazing, as usual, and contextual presentation. So thanks a lot. This was really illuminating. You had a slide about the stress test, which showed me something that I think is like a hint of how this would end up in production. So I'm looking at the two top left corners, right? And they have, you see there's some areas where minification and magnification are mixed. And you have two separate recommendations for how to filter them. So what happens in an area where there's like a close intersection, right? Where a tile that is minified is supposed to be next to a tile that is magnified, and or it's the same tile and you have like a strong gradient there. Blending isn't enough because the metalness suddenly can't be evaluated the same way, and basically you have to change your evaluation model. Do you have any recommendations? Have you thought of how this actually gets deployed?
So we don't do any branching in the shader or code. Minification and magnification are always handled together, and it's based on this observation that when you're minifying, you're jittering in screen space when you project it to texture space is going to be dramatically higher than any single texel jitter, and vice versa. If you're magnifying significantly, then your texel space jitter will map to many pixels. And when you are around MIP 0, then both of jitters are going to be very similar in magnitudes. And one thing that we discussed, but we have not tested, and I haven't thought too much how to realize this in practice, would be to somehow either correlate or rather decorrelate sequences used for jittering in screen space and texture space, because right now they are two completely different blue noise sequences. So I don't know how they interact with each other, and we have not investigated this too much. But from the perspective of both temporal filtering and spatial filtering, but also how we handle this, there is no difference in handling. So this recommendation of sometimes using stochastic texture filtering for some assets or the others. It's again, it's something that would not really affect minification at all, because it would still be present. And I don't know if this answers your question.
Partially. No, it does. Like, yeah, it does tell me that actually deploying it won't be that difficult, which is the point.
We're trying to actively deploy it. Yes.
All right. Well, let's thank our speaker again, and then. So our last speaker is Andre. I'm gonna get this wrong. I forgot to ask you. Chabarro. All right. He is a PhD candidate at McGill University. His thesis research focuses on computer vision, namely representation learning and image quality assessment. Andre has also worked on several computer graphics related projects involving neural representations, neural radiance fields, and sign distance fields.
Hi, so my name is Andre Chabarro, and my talk is actually about two of our papers. The first one is titled Contrary Supersampling for Sign Distance Field Rendering, which we presented at Graphics Interface 2023 conference. And the second paper is its extended version, which we submitted to TVCG Journal, which is titled Contrary Supersampling with Subpixel Edge Reconstruction. My co-authors here are Yangyang Zhao and Ruby Rao from Huawei Canada, and Derek Naruzarai and Paul Cry from McGill University. So we were initially working. We were doing some other work involving sign distance fields, or SDFs, and rendering SDFs is usually done with sphere tracing. We realized that one of the only real anti-aliasing solutions that we can use directly for SDFs is to use supersampling, but it's often too computationally expensive, and so we wanted to have a better approach. And also, most of the existing optimized solutions are intended for mesh-based representation, so they can't really be applied for SDFs. And in this work, what we propose is contrary supersampling, or CTSS, as well as subpixel edge reconstruction, or SER, which together form a very efficient direct spatial anti-aliasing solution specifically for rendering sign distance fields with sphere tracing. And unlike previous work, this is supposed to be a video. And unlike previous work, CTSS is very easy to implement. You can fit it into your sphere tracer very easily. It doesn't need casting any additional rays per pixel, and it doesn't need any offline pre-filtering of appearance. So nothing complicated. It just adds to the code. And in terms of performance, it only adds about 25% computational overhead as opposed to supersampling, which essentially multiplies your performance. And the image quality is essentially comparable for most specifically geometric edges. Well, for SDFs, what do they do? They define an object implicitly. They encode the distance to the object surface, and with that, they can describe different topologies of varying complexity, from very simple to very complex. And in modern graphics, SDFs are used for things like global illumination, shadowing, collision, sometimes some certain volumetric effects, but they're also quite handy in deep learning because they're continuous and differentiable. And they can be expressed as either a combination of mathematical functions, or they can be even directly encoded with neural networks, also pre-computed in voxel fields and so forth. But to render SDFs directly, we use sphere tracing, which is an iterative approach. It's an algorithm that converges to the zero value isosurface of an SDF. Eventually, after some number of steps, it will reach the surface by ray marching in steps equal to the current SDF value. So SDFs encode distance, and we take that distance and we converge to the surface. So the original paper on sphere tracing actually considers its application to anti-aliasing. You see, since SDFs, they make cone tracing very easy to do, because then you just need to compare the cone radius to the current SDF value. And when you combine that with appearance pre-filtering, you can do some special adaptive sampling schemes as well to essentially consider volumes as opposed to just points. So you can reduce aliasing by integrating what's visible within a volume as opposed to just visible along a particular array. So with a method termed differential cone tracing, what we do is we render and then composite cone elements for a given pixel, and then each of these cone elements has a distinct color and orientation, so you can composite them into a single color, which will be basically the integral of what's visible. More recently with NURBS, there's also methods, for example, MIP-NURB, where they don't necessarily render points in space, but rather conical frustums, and they predict visible color within a pixel as opposed to just visible color along a given ray. So with CTSS, what we do is we extend sphere tracing and we perform supersampling along the traced ray as opposed to in pixel space. So we detect surfaces with partial visibility within the pixel, and we do this by essentially tracing a cone through a pixel, and then we evaluate cone intersections to detect proximity to the local surfaces. And as I said, this is very simple with SDFs because we just compare the cone radius to the SDF value, and a surface is essentially visible if it interacts with the cone, if it intersects with the cone. So a pixel obviously can contain multiple partially visible surfaces, and so we basically want to integrate them for proper aliasing, anti-aliasing. So we can't just sample color at every iteration of sphere tracing because that would be impractical. That would be just too slow. So what we do is we first identify what we call hit groups, and these are segments along the traced ray with consecutive partial cone occlusion. For example, on this figure here, there are three. The surface is the blue blob on the bottom, and here we have three hit groups where the cone intersects with the surface. In each of these groups, we identify them by the hit point entry and the hit exit points along the traced ray. And then even though these segments are on the traced ray, not necessarily on the surface, what we find is that we can sample from these segments to actually collect the visible color. And so we actually find that just using one sample per hit group gives us sufficient information to represent color within a pixel. And so in this example here, CTSS will collect just 3 samples for this particular traced cone. Just to visualize for a very simple scene here, some simple geometry. Typically, partial cone intersections, they'll happen at the object contours. I hope it's clear enough on this projector. But basically, partial cone intersections will happen. They occur near object contours, and that's where the edges will happen, and that's what will be appearing jagged, and that's what will be suffering from aliasing. So this figure here is basically showing where CTSS will collect multiple samples. It's precisely near object boundaries, and that's essentially what we want. So CTSS by itself, it's really good at anti-aliasing the silhouettes of objects when rendering signed distance fields. But we also need to aggregate the samples based on some sort of visibility-based weights. And if we simply average the samples, then we get this result kind of similar to extrusion, where the object edge is essentially detected further away from the actual surface, and that's not what we really want. On this figure here, I'm showing different traces with different size cones. So for example, a cone can cover not 1 pixel, but multiple pixels. And for the uniform weight sampling, what you get on the figure D, that's you basically get the edge being just extruded from the object. Instead, what we do with CTSS, we compute a visibility-based weight, which was what we show on the E figure, or the W5. Here, we take into account the visibility of a surface when we actually aggregate that sample. So for each sample, what we define is the visibility based on a metric called cone occlusion. So we illustrate here in the circular cross-section of a cone, how traced surface intersects with the cone. So basically, the cone occlusion will range from 0 for just very small intersections to full cone occlusion for almost the entire cone. It's defined by a simple equation. I'll skip this, but it's quite simple. In theory, what we're actually doing is, as we are iterating with sphere tracing, every intersection will essentially start with a partial cone intersection, and then it may end up with a full cone intersection at some point, or it may just move on to the next hit group. So cone occlusion basically approximates the visibility of a surface, or how much of the trace cone is occupied by that particular surface. And so we define our visibility weights based on that. What's another thing that's important is that earlier intersections will actually occlude the later intersections, and so we need to correlate the sample visibility and not just estimate their individual visibilities. So to achieve this, we model the local visibility of a given surface over the 2D cross-section of the traced cone, and we do this from the perspective of the current pixel, as was done in prior work with differential cone tracing. But we assume that the macroscopic surface is locally planar, which means that the surface, when viewed through the pixel, is basically a plane. It's valid for most geometry that's larger than a pixel, but obviously for small geometry, that's a limitation of our method. But essentially, the surface will form a half space within the pixel, and so we know the orientation and the coverage of that particular surface because we know the SDF value, we know the normal map, we know the normal vector, and so we can orient the surface within our trace cone. And then we can test against this half space to basically describe the local visibility within the pixel. What we do is we just model this as a very simple equation of, it's a first order polynomial equation of form y equals to ax plus b. The surface is basically just a line. And we parameterize this with the SDF and with the normal vector. So then we pack this visibility into a 32-bit integer because, in shaders it needs to be pretty easy to compute and optimize. And the ones in this bit mask will actually mean that the surface is covering that particular point within the pixel. And the zeros obviously is the clear space, nothing there. And we use a 6x6 mask, which makes 36 bits in total, but we omit the corner bits, so it makes for a 32-bit in total. We compute this in real time, and it's very simple. We basically divide this into 6 rows of our bit mask, and then we solve for the relative coverage over each row, and then we just convert that to bit shift. So basically, if the full mask is 6 ones, then if the coverage is half, then we need to shift that to the right or to the left by 3 bits. And once we have our bit mask, everything just becomes Boolean logic. We can apply Boolean logic to correlate the samples. So we just need to OR 2 bit masks, and then this is relevant for us because we need to correlate the visibility between samples in an efficient way, and we need to discount the visibility of later samples which are occluded by earlier surfaces. And so going back to the example seen from earlier, let's just look at some zoomed in patch. So with no anti-aliasing, we have something like this. And then when we simply average results, that's what I showed before, we get this extruded edge example. We get this effect of extruded edge. I'll just alternate between them. And then when we actually apply our visibility-based weights, you get a much nicer looking edge, and this is what you expect to have for a proper anti-aliasing. Once again, this is where we collect the additional samples, so CTSS will not be applied to anything else. And if you compare that 4x supersampling, for example, supersampling is uniform across the entire image, but then again, performance of that is going to be quite bad. Obviously, in our case, since we have to render a lot fewer samples, then the performance is, on average, it's only about 20% overhead compared to supersampling, which would multiply the performance, the frame time. But there are obvious limitations to CTSS alone, and so that's what we're going to address with an additional stage, which I'll describe in a bit. So just to go over the limitation of CTSS alone, here in green, we're showing the correctly anti-aliased external edges. In red, we have the edges that are undetectable by just cone intersections. And in yellow, we have non-anti-aliased color that comes from color discontinuities like shadows, textures, or specular highlights. Those we cannot do because we are mainly focused on geometric aliasing. And so to conclude, CTSS is a method of geometric aliasing, anti-aliasing, but it does not anti-alias color discontinuities. So on top of that, it doesn't anti-alias all of the depth discontinuities, just some of them. So with the help of cone intersections, we can identify what we call external edges. Those are the visible depth discontinuities that occur at object contours. But this strategy doesn't reveal what we call internal edges. Those are the edges that are found in relatively flat regions. And so we introduced an additional stage called subpixel edge reconstruction, and this brings anti-aliasing to internal edges on top of what the previous implementation with CTSS. So SER, or subpixel edge reconstruction, or SER, it detects internal edges and then it also resolves them by evaluating a potentially additional sample at the points where CTSS is basically terminates. So first we need to identify internal edges. So in our case, what we do is we look at SDF normal vectors computed with finite difference at different scales. For SDFs, normal vectors are computed with finite difference usually. And so we just need to control the epsilon value, which essentially controls the precision of that. And for flat surfaces, if there is no edge, the small and the large scale, they will the small and the large scale normal, they'll basically give you the same exact vector if the area is flat. But then if an edge is present, then there's going to be some disagreement because the large scale normal is basically a blend of all the local normals in that area. And so we can simply compare them with cosine similarity, so the small scale normal and the large scale normal. And then on the figure here in the middle, we are showing the cosine similarity of these small and large scale normals, and they basically disagree precisely at the edges, where the edges are found in an image. And that's how we detect them. We just basically threshold on cosine similarity between, computed in this way. So we model the edge in the 2D footprint of the pixel from the perspective of the traced cone, and we follow the same macroscopically planar assumption as with CTSS. The edge is basically modeled as two planar surfaces, and then we call them the primary and the secondary sides of the edge. And that's what we essentially refer to as subpixel edge reconstruction. Here we need to kind of reconstruct the edge, and then we need to evaluate the visibility of the primary and the secondary sides, and then evaluate the color and then weight appropriately. So in other words, we need to evaluate the intersection between these two surfaces. And so in 3D, this can be quite complex, but our model projects everything to 2D, which makes it a lot more simple. So we reparameterize the problem from a different perspective. Now we view it from the intersection. Now we view the intersection orthogonally to the ray direction, and orthogonally to the ray direction and not across the circular cross section. And then the two surfaces are modeled once again as two lines which we can intersect, and once we compute that intersection, we can get the visibility of each one of these surfaces. This setup follows the same exact logic as we applied with CTSS, where we have our cone occlusion, except here we have this intersection point that essentially controls the visibility of the two sides. So first, what we do is we define a search direction. CTSS itself will give us the primary sample at in the center of the traced cone, but we need to find where the secondary surface will lie within this cross section. And it's actually kind of hard to see, but the circle should be blue because that's the red part is the secondary surface, but the blue part is the primary surface. And so we first need to make an educated guess as to where the secondary surface lies. And we find that by looking at the difference between the large scale normal and the small scale normals, we can actually make a good guess as to where the secondary surface lies, because the large scale normal is basically a blend between the two. And so it will give us some good geometric clues as to where the secondary surface lies. And so we define the search direction, and we look along that search direction within our cone, and we evaluate the normal at that point. And so then we basically have the normal of the primary surface, we have the normal of the secondary surface, and then once we know that, we can intersect them properly. And that's the pixel edge reconstruction. We've resolved the edge, and we know where the primary sample is, we know where the secondary sample is, and since we have computed the intersection between them, we also know their relative visibility. So now, just to compare the image quality, we have here a simplified Sponza seam, which is a SDF-based representation here. As I said before, CTSS will anti-alias silhouettes, or what we call external edges, but it can only detect those particular types of edges, not all of them. So SCR basically complements CTSS to kind of bring anti-aliasing to both external and internal edges, kind of completing our solution as a two-part method. So the image quality is comparable to supersampling for most geometric edges, for specifically, of course, for those that it can detect, which is for CTSS and SCR, it's basically all of them, except, of course, those that come from colors, textures, shadows, and specular highlights. But as long as the edge is caused by geometry, then it will essentially be anti-aliased. So for actual performance, we've obviously done a lot of evaluations for this for different types of scenes and different complexities. But to summarize things, if we compare it to just sphere tracing alone, which we refer to it as no AA, like no anti-aliasing, for 4x supersampling, the frame time would actually go up by a factor of 4. But for CTSS, it's only 20% over that. And with CTSS plus SCR, it's about 165% of the frame time. Once again, the image quality is comparable or even better for some edges, especially for CTSS because of the way that it detects the visibility within the pixel. SCR can have some issues, which are parts of its limitation. For example, it can sometimes fail to find the secondary side of the edge, but in most cases it works quite well. Obviously, the other limitation would be, since we assume that the surfaces are microscopically planar, anything that is basically smaller than a pixel by a lot, if there's a lot of variation there, then we can't model that. So yeah, I guess I'll stop here. With that, just to summarize, we have CTSS and SCR. Together, they form an efficient spatial anti-aliasing solution for signed distance fields, and we offer comparative quality for most geometric edges while just requiring a fraction of the computational cost involved with supersampling. And with that, my presentation is done. Thank you. We also have a shader toy example to play around.
Great. So questions? Well, I have maybe a dumb question, but with the SER part, I was just curious, like, if you decided, I don't want to figure out this convex versus concave, what if I just did convex? What kind of errors would show up?
That's a good question. So, in fact, I forgot to speak about that completely in my presentation, but all it does is it basically tells you, so we need to know that information to actually properly find the secondary side of the edge, because it dictates which direction to look at. So in our case, we find that for convex edges versus concave edges, the direction is essentially reversed. So we find if the edge is convex or concave by evaluating the curvature, which is done quite easily for SDFs. It basically reuses the same SDF evaluations as we had for normal for the normal vector. But if you do that, if you ignore the curvature of the edge, then you will end up looking in the wrong direction.
Okay, that makes sense.
So that really points to where you need to look. So that search direction is specifically defined based on the curvature of the edge.
Okay. Thanks.
Hi, thanks. Really great work. I may have completely misunderstood the SER, the second thing you talked about. But if I haven't, then is there a problem if there are 3 surfaces or even 4 surfaces in a pixel? Is it a problem, and does it matter? Can you see it anywhere?
Yeah, that definitely would cause issues with SER, because essentially SER only models two surfaces. We could consider something more complex than that, but that would, of course, require to basically expand this whole solving algorithm into multiple steps. But as long as you can define the visibility BIS masks for each one of these surfaces, then I think it'll be okay. Maybe you can decompose them into multiple steps, so you would just consider pairs of them. Maybe you can find an ordering for them and then kind of overlay them together as well. But yeah, in this current stage, we only consider 2 surfaces.
Okay, I think that's it for questions, and that ends our last session. Let's thank our speaker again.